Hi there. Hello. How to do a cross-sectional ordinary least square regression analysis in Excel. I know a lot of people who frequently use regression analysis as part of their work. And many of these people are of the opinion that you can't feasibly do a regression analysis in Excel. But I kind of disagree with that. In this video, I'm going to show you 6 ways how to do regression analysis using Excel. Now, that being said, it is substantially easier to do this in more dedicated software, such as Stata, eViews, or R, or Python, or whatever. It's easier. But if you are the type of person who feel that you should put regression analysis on your resume, on your list of skills, or you want to claim that you know regression analysis on a job interview, then I kind of feel that you should be able to do it in Excel, just in case the need ever arises. So let me show you the data set we're going to work with. It is real data, but also very limited in scope, just so it could be easy to copy paste this. And I'm a lecturer. And when I lecture, I have presentation slides, and I make these slides in LaTeX. So I wanted to know, can I use the number of slides in order to predict how many lines of LaTeX code there is that created this set of slides? So here is the 14 last lectures that I have done. So for instance, in one lecture here, we see that it had 85 slides. And it had a LaTeX code that consisted of 2,882 lines of code. So I want to create a model here where I predict how many lines of LaTeX code are based on the number of slides. Now you could of course make an argument that it should actually be the other way around. This is reverse causality, but it doesn't matter. So this is essentially the model that I want to run. And let's go through the 6 different ways that I can think of at the top of my head in order to do this. The first method is pretty simple. You just make a scatter plot, and then you add your trend line, and then you just show the equation. So I already done that and done a little bit of the formatting, but let's see how that can be done. So let's just select the data like this, and then we go to insert, and then we go to scatter plot over here. We can choose this. So this gives us a plain scatter plot. Now up in the top right corner here is this plus sign. If you click on that, you have the option of adding a trend line. And if you click on this black triangle, you get some further options. And there you can choose to display the equation and also the R squared if you want. So as you can see here, this is the regression result. So this is a univariate regression, and it gives us a beta 0 of 576.49, and it gives us a beta 1 here of 29.806. So the first one of 576, that's like the intercept, and this over here, that would be the slope, and also gives us the R squared. So this is a very nice and easy way to do it. Just make a scatter plot. Now there's a mistake that is commonly made. So when I do give this as an exam question and students use this approach, what typically goes wrong is that the y variable and the x variable is confused. That you mix them around and get different results. So let me just copy this data down here, and this just switch around the y and x variable. So what many people do, they will just select the data, and then they will add the scatter plot, as you can see up here. We can add it, and then they add the trend line, and they add the equation. There we go. Let's see. They add the equation and the R squared. As you see now, the results are different. Rather than getting a slope of approximately 30, we now get 0.0261. So what has happened here is that the y variable and x variable has been switched around. You see here we had scale in thousands on the y-axis and hundreds on the x-axis. Now suddenly it's the other way around. We see that lines of code has become the x-axis, and number of slides the y-axis, so it's been switched around. So this is a very common mistake that is made. So let's look at our second method here, and that is to recognize that these coefficients, there are equations behind them. So for instance, this is well known, the slope coefficient is equal to the covariance between x and y divided by the variance of x. So we can simply just use the covariance and variance function in order to calculate it. So as you see here, we get beta 1 equal to 29 by just taking covariance and divided by variance. Now there are two mistakes here that are really commonly made. Again, I literally seen hundreds of students try to do this in my course. So when they use this method and when they get it wrong, it's usually for the following two reasons. One reason is, again, that you can mix around the y variable and the x variable. Now this doesn't matter when it comes to covariance, but instead of dividing by the variance of the x variable, the right-hand side variable, what they often do is divide by the variance of y. And then you get different results that you don't want. Another common mistake that they do is to confuse sample with population. There are two different versions of covariance and variance and standard deviation and many other of these statistical functions. You have one version that is for the population, another one that is for the sample. And we need to always use the sample version. So notice here that it says covariance.s instead of covariance.p. P is for population, S is for sample, and you always need to use sample. So the difference is that instead of dividing by n, that will be population, you divide by n minus the number of parameters to be estimated. That is the difference. If you know a little bit of statistics, you know that covariance is somehow related to the concept of correlation. So that means you can substitute covariance with an expression containing correlation. And if you do that, you will get an alternative expression for the slope coefficient. And that is the correlation between x and y multiplied by the ratio of the standard deviation of y and the standard deviation of x. So instead of using covariance and variance, you can use correlation and standard deviation. So that's an alternative way of calculating beta 1. Once you have beta 1, you can use that to calculate beta 0. So the function for beta 0 is just y bar, the average value of y, minus beta 1 hat, which we calculated up here somehow, multiplied by x bar, the average value of x. So function-wise, we use average, and then refer to beta 1, and then average again. So this is pretty straightforward. We're just using different functions in Excel to implement the equation for beta 1 and beta 0. Now my third way to do it here, and it's not really any logical order through my approach there, is to use just use a function in Excel to just calculate it outright what these beta coefficients are. And that is, in the univariate case, we have the slope and the intercept function. So the slope function, well, I will calculate beta 1, the slope. And intercept will calculate where we intercept the y-axis of beta 0, the constant term. So just very straightforward, slope, and then you provide the variables. So again, the common mistake here is of course that you change around the x variable and the y variable. Common mistake. Next, method number 4 is kind of different because so far our three methods have only worked in a univariate case. They only work when there's a single variable. Now there are technically two coefficients to be estimated here. So some people will say that this is bivariate, but I will say that it's univariate because there's only one regressor, even though there are two coefficients, because you include the constant term. But what if you have more than one regressor? In that case, it wouldn't work what we've done so far. But what would work is to use array functions. So the slope coefficient is equal to covariance by the variance. But if you've done like a course on econometrics or regression analysis or statistics, you know that we can solve this with the matrix notation. So that is the beta vector, which is a k times 1 vector, is equal to xt times x, and then take the inverse, multiply by xt and y. So X is this data matrix. It's an n times k, n observations and k variables. So here k is actually equal to 2 because we have a constant term. So you can actually implement this with functions here in Excel. So if you look here, we can use the mmult to do matrix multiplication. We can, let's see, let's close that and try to show the whole thing. We can use mmult, which is matrix multiplication, to multiply the matrices together, to multiply xt and x together, and to multiply this together with xt and y together. We can also use min inverse or m inverse, sorry, that is matrix inverse, to take the inverse of this thing. Transpose to take the transpose. So by combining mmult, m inverse, and transpose, we can actually implement this equation for multivariate. Now, so when I was a student, I saw this equation quite a lot, but lecturers never showed us how to actually implement this in Excel. So what they, maybe this was just so obvious that there was no reason to mention it, so maybe I just stupid it that way. But when I implemented this in Excel, it didn't really work until I realized you actually need to have an additional column here which represents the constant term. So we have an extra column here that just goes 1, 1, 1, 1, 1, and that is essentially just a constant term, right? Without this, this wouldn't work. So you only you see you get two numbers there, but I only type it out once because the output is an array. So you type in this, and it will automatically give you 2 cells here, or k cells here, depending on how many explanatory variables you have. Now, back in the day, it used to be the case that you had to click Control-Shift-Enter in order to activate this function. But that's not the case anymore. You can just click Enter, and it will be implemented, even though it's just an array function. Next method here is also can be used for multivariate cases, and that is the linest array function. And the output here, so we have linest, we type linest, we have the let's see, what's that, the y variable and the x variable, and then we have a parameter that is set equal to true because we want the constant term to be calculated in a normal way or the standard way. If we set this parameter to false, then it will arbitrarily force the constant term to be equal to 0, and usually you never really want that unless you have a very specific reason. So by default, don't do that. And then finally here we have our parameter is true, and that means that it will provide us with extra additional statistics. So you type this, click enter, and it gives you this whole matrix here. And the problem with this matrix is that it's not really easy to know what exactly these different numbers are. So you kind of actually need to go to online and find the Microsoft Excel documentation, linest, to figure out what these things are. But on the first row here, we have the beta coefficients. And I think it starts with the highest one. So if we had 3 regressors, then it would be beta 3, beta 2, beta 1, beta 0. So right here we have beta 1 and then beta 0. Directly beneath them we have the standard errors. So beta 1 is 29.8 and its standard error is 4.6. Now the number between that again, over here, that is the r squared, that's the explanatory power. So the number between 0 and 1, in this case, now 77. So 77% of the variation of the data is being explained here. Over here, you have the standard error of y. Here you have the f statistics, degrees of freedom, squared sum of the residuals. No, so that's over here, and here is the s squared sum. Don't remember what that is, to be honest. So I've done some color coding here, and over here you can see what exactly it is. As I said, the beta coefficients on top here, the standard errors, the r squared, standard error of y, the f statistics, degrees of freedom, SS reg, and SS residual. You don't really need these numbers. It's nice to have the r squared, I think. But SS reg and SS resid, those two are used to calculate the r squared, as you can see down here. So if I take SS reg divided by the sum of SS reg and SS resid, then that will be the r squared. So kind of redundant to have this. And the standard errors is usually not what I'm interested in. Usually I want the actual p-value. So this table does not calculate the p-value for us, but we can calculate it based on the standard errors. So just to do that very simply here, what we do, we take the the t-distribution with two tails, and we have the first input is going to be beta divided by standard error, and then the second input will be the degrees of freedom. So this is how you actually can calculate the p-values. So for instance, the p-value of beta 1 would be input into this two-tailed distribution, two-tailed t-distribution I mean. We have beta divided by standard error of beta, and then we have the degrees of freedom. And the degrees of freedom we can find right here. That in this case would be n, which is 14, minus 2, because we have beta of 1 and 0. So 14 minus 2 is 12. And so yeah, this is a pretty nice way to do it, I think. The only problem with this method is that it's kind of hard to remember what these different things means, so you kind of have to look that up every time, unless you have a good memory. The sixth and final method here is to use the tool pack. So right here we have the data, and we have some output here, and it came from, let's see, if you go to data and go to data analysis, and then we have let's see, regression. So data analysis or data toolpack, this thing is not always activated, same with the solver and the developers. You might have to go to options and go to add-ins and then activate it. But assuming you have, let me just show that one time. Go to data, go to data analysis, go to regression, okay, and then input y range, that would be the lines of codes. And then the X range, that would be the number of slides. And then the output range, let's see, we can put it over here, for instance. Click OK. And then it runs the regression for us. So here it gives us the R squared, for instance, adjusted R squared. Here we have the beta coefficients, and then the T statistics, standard errors, the p-values. So as you can see here, p-values is the same as we calculated over here, so that is good and nice. So yeah, that's 6 different ways to do regression analysis in Excel. And by regression analysis I meant, of course, cross-sectional, ordinary least square. So just to recap quickly, you can make a scatter plot, add the trend line, and then add the equation. Remember not to mix around y and x though. You can calculate this using the covariance and variance function, or the correlation function and the standard deviation functions. Or you can use actual functions there, slope and intercept. Or you can do matrix multiplication on your own. And this I really don't recommend to do, because it's kind of tedious to type this out. And in personal experience, I usually get this wrong myself, and on the first attempt usually. So you need to try. Then we have the nest and error function, which is my favorite actually, to be honest. Finally, we have the toolpack data analysis, where you can use regression analysis.